We've looked at arithmetic sequences where the terms go up by a fixed amount. Now we'll look at a different kind of sequence, geometric sequences. In this case, let's start with the example of cells in a dish. Imagine that you start off with 3 cells and they are doubling in quantity every minute. So at the beginning there are 3 cells, then later on after a minute there'd be 6 cells, and then there would be 12 cells doubling every minute, then to 24, then to 48, etc. You can see that this sequence doesn't go up by a fixed amount every time. If I write it as a list of terms like this, the first term is 3, then second term is 6, etc. Well, let's describe what's happening here from this term to that one. Here I am doubling. Again, I am doubling. Again, I am doubling. And so forth. So you can see that what's happening here, the thing that happens from one term to another is that it is multiplied by something as opposed to something being added. This means I can start working with my terms down here. 6 is the result of taking 3 and doubling it. 12 is the result of doubling 6, which itself was doubling 3. So I'll write 3 times 2, that was the 6, times 2 again. 24 was the previous thing, all of this, times 2 again. And this is whatever I have had just before, times 2 again. So, what can we do with this? Let's look at it a little bit further. Of course, my objective is eventually to find the nth term, an expression, a formula for the nth term. So, well, if I see this one here, 2 times 2, that's quite obviously 2 squared. I can rewrite it like this. This will be 3 times 2 to the power of 3. And this is 3 times 2 to the power of 4. If I continue the pattern upwards here, well, this is actually 3 times 2 to the power of 1. And actually, 3 could be written as just 3 times 2 to the power of 0, since 2 to the power of 0 is 1. If I wanted to go for the next term, T6, I could use the patterns that I find here. This should be 3 again, multiplied, well, the next one's going to be 2 to the power of 5. Notice here in the red that the power here seems to be always 1 less than the term. So this gives me an idea for my nth term. Well, I always have the 3, and then the 3 has been doubled n minus 1 times, 2 to the power of n minus 1. With this sort of result, I could answer now questions like how long, or how many cells rather, cells will I have after 10 minutes? Well, n will be 10 since I'm counting in minutes, so I'm looking for T10. I will substitute in my formula 3 times 2 to the power of 10 minus 1. That's 3 times 2 to the power of 9, which is 3 times 512. And so I will have 1,536 cells altogether. So let's generalize to more general cases. Let's imagine that I have the sequence a times r, then multiplied by r again, then multiplied by r again, etc. Let's write it out like this. My first term is a, then a times r, then a times r squared, a times r cubed, etc. What will be the nth term? Well, by comparing the exponents, 4 and 3, 3 and 2, 2 and 1, etc., we can quite easily see that the general formula will be a times r to the power of n minus 1, where r is the number that I multiply with from one term to the next, times r, times r, times r. This is a geometric sequence, and this formula applies to all such sequences.